13 and 14 on your thumb drives. It is about chemical equilibrium. It does more than gaseous, but we're going to start with gaseous. The equilibrium constant, we've talked about this before. I don't know how much you've remembered. Come on, this is, whoa, whoa, whoa.
And that was really fast.
Okay, so basically, it takes a generic equation, which is right here, okay, and yeah, all the computer systems are laggy today, and converts it into this. Now, if it's pressures, it's written this way, where, for instance, if one of these was water, I would go the pressure of water, and it's really, yeah, it's really lagging, okay, and then I'd put it to the power of whatever the coefficient was. So say if it was a 2, I'd put a 2 up in the exponent place, and it will eventually show up. There we go. So I would put that in here. That's if it's a pressure, if it's a gas, okay? If it's not a gas, then we use concentrations, and concentrations are used in brackets. So I would put water, concentration of water, which really isn't a thing. So let me do a different one. It's not going to let me erase. Okay, so say that I did CO, okay, not CO. Let's try over here, CaCl2. If I want to do the concentration of that, I would put it to, say, whatever the coefficient was, say it was a 3. Now it's being really slow. So those are concentrations. These would be aqueous in green, and the black would be something that I would put a gas in, okay? So it's always the coefficient is the power. So here, just remember that. Products, again, are on the right-hand side of the equation. The arrow always points to it. If it's a one-sided arrow, we're going to go into things that are two-sided.
They're at equilibrium.
They're at equilibrium. And this should actually have a two-sided arrow in it that is not showing, but finally there it is. It should have a two-sided arrow, because when we do an equilibrium expression, we are going to be able to push the equation one way or the other by increasing the pressure or doing something to it. So let's go forward, maybe. This is really irritating. And there it finally goes. Okay, so this is a partial pressures. We're talking about the right side and left side. Partial pressures are in, so it's products over reactants. Each partial pressure is raised to a power, and we talked about that. Oh my gosh, this is being so slow today. Okay, so changing the form of the chemical equation. The expression for K depends on the form of the chemical equation is written into. When the coefficients are changed, coefficient rule, if the coefficients in a balanced equation are multiplied by a factor of n, then the equilibrium constant is raised to the nth power. So if I multiply an equation through by 2, then I'm actually squaring whatever the coefficient was. Okay? Whatever you feel like you need. So here's an example. So the chemical equation, come on, between hydrogen gas and chlorine gas will give us hydrochloric acid gas. The equilibrium constant would be the products over the reactants. And since they're all gases, I use P's. Okay? If they weren't, then I would use brackets. Hopefully it's going to, I'm going to pause this first. It's been that kind of day. All right, so we're going to try going forward. So if I went a half of everything, so again I'm cutting it in half, then when I do my K1, my constant, I would put the halves in. So with constants, with kinetics, I can use halves to balance equations. Only with kinetics. Only with kinetics.
Only. So
okay.
Where it says like PHCl, that's just saying the pressure of that gas.
Right.
So
now the reason why it would do this is if I wanted to find the K to make 1 hydrochloric acid. Okay, 1 mole. Okay, so going forward, I'm going to go through this hopefully fairly quick. So you'll notice that K2 will actually end up being a square root of K1.
Because it's raised the half.
Right. Okay. So this right here is bromine. When the directions of the equation are reversed, and this has been used on AP questions a lot. Okay, the reciprocal rule. So instead of saying it's K1, if I reverse the reaction, it becomes 1 over K1. Okay? All right, moving forward. All right, so here's another example. We've got it going backwards now, so we would write the K backwards. So we'd have the pressure of H2 times the pressure of Cl2 divided by the pressure of HCl squared. If I was going to do it a half again, so I only had one that was decomposing, then I would half those. Okay, and it just shows there it's 1 over. Adding chemical equations. Rule of multiple equilibria. So if I have a lot of equilibrium, they've done this before on things. So I've got Ka, I've got Ka1, Ka2, Ka3. And you'll notice when we start working with Ks, they'll have subscripts. The subscripts are just generally to tell you what's going on. Ksp would be K of solubility. So you're taking and dissolving a solid. Ka is K of an acid. Kb is K of a base. Kp is K pressure. Kc is K of concentration. Just a normal Keq is just a general. Okay, so there's a lot of Ks. We do them all the same. Products over reactants to the power of their coefficient. Okay, so the mathematical relationship here, if I'm adding, so I have a reaction 3 is equal to reaction 1 plus reaction 2. If I add them, then what I'm going to do is I'm actually going to times the Ks. This is going to be different in thermal. K is the equilibrium constant. So if I have a reaction and I can take two reactions and add them up to get that reaction, then I can take that two separate Ks, multiply them together, and get the K for that reaction. Now thermal is going to be different. When we get to thermal, it's going to be a little bit different there. So you got to keep the two separate. Okay, so heterogeneous equilibria. If I have both liquid and gas phases, okay. Homogeneous when I have the same phase throughout, heterogeneous when I have different throughout. Usually when we have heterogeneous, we use KEQ. When we have the same phase, we tell what it is. Kc is concentration, Kp is pressure. The position is dependent on the amount of, is independent of solids, liquids, or, so the solids and liquids drop out of Ks. We don't write them. They just disappear. We just pretend like they're not there. They don't affect it. Okay. So here we have, does anybody know what this is? Iodine. Okay, and iodine will sublime. Go directly from a solid to a gas, and you need to know that it's a purple gas. And it will sublime at room temperature, meaning just that, going from a solid to a liquid. So writing the equilibrium expression for heterogeneous mixtures in terms of, for solids, again, and liquids don't need to appear. Only ions and molecules that appear in the solution expression for K. Concentration again, in brackets, that means molarity, moles per liter. Okay, so here we have an example again. Write the equilibrium constant expression for K. I want you all to try to do this. I'm going to stop right here. For the reaction between sulfur dioxide gas and oxygen to produce sulfur trioxide. So you should be able to take that, put it into an equation right now and balance it. So do that and write the K. So write the equation for it, then balance the equation. And you can use the back of your papers because they're blank if you want to. Oxygen gas, which is Braunhifkel. I'm going to pause the video while you do that. Thank you. I really am having issues today. Kp is pressure. Kc is concentration. So here's our equation. You should have had that balanced.
Got it.
Okay.
It is necessary to be able to have the crystal before the expression for K is.
There we go.
Boom, did it. Oh, shoot, no, I didn't.
Okay, products to their exponents, their coefficients as exponents divided by reactants. And these are times together when you get down to the bottom. Okay? Now, big problem that I saw as a reader is kids would set this up right, but when they put the stuff in, they would go this squared divided by this squared times this. Where does that put this? Up here. So you got to make sure you put this in the bottom in parentheses. Okay? Either that or put the bottom in first, get an answer, do 1 over x and times it by the top.
So could you just put the whole thing
in parentheses and then just put times in between them?
Yeah, the bottom right here would all need to be in parentheses. And it's not going to show that I put parentheses there. There we go.
No, because you're only doing the
Just SO2 and SO3. So we take those, we take them from here. We take them from the coefficients. Okay? Is everybody okay?
You're not going to get any halves.
Right, unless it tells you to then, I only want one of these, then you've got to take it down. Yes?
So will it give us the pressure, or will we have to?
We're going right into that. Okay, so if you balance the same equation the following way, so this is what you were asking. So I could balance it this way. So if they said I only had one SO2, so I'd need to figure out what the equation was balanced with just one SO2. So then I would use the half. And since I use the half, the K would be a little bit different. Okay, both expressions for K are correct. Okay, both will provide you the right K. All right, so determination of K's. There's 3 ways to calculate K, and this is what we're heading into. Given the partial pressures of the product, you just plug them in and chug. Okay, you get the answer. But what happens if the pressures do not have to be, okay, they don't have to be expressed in a specific unit because K has no units. Okay, K has no units.
But it is K.
They all need to be the same, but K has no units. Okay, so equilibrium mixture, here we've got one. Okay, now, at 990 degrees, it's analyzed and found that the partial pressures of blah, blah, blah are this, this, and this respectively. So this is just a plug and chug, right? I want you to take a minute, set up the K. Is it balanced, first of all? Is it balanced?
Hold on.
Yes, it is balanced. So you want to plug in and chug and get an answer for me at K. K is dependent on temperature.
Oh, no.
K is dependent on the temperature. So really quick, this would be one of your 60-second questions.
So,
Plug it in, get your calculators out. You're going to need them.
figure it out for people.
No, come on, Colin, get a calculator out.
But it's so far away.
Okay, so here we go with an answer. Let's see if you got the answer right.
Wrong.
Come on. And the board will decide when it decides to plug in. So there's your K. Now you plug in any day now.
I screwed up.
How do we do? Remember, this bottom part, when you get your divide sign, has got to be in parentheses.
Yeah, so just do 0.611 times 1.6.
I was always taught to do the bottom first, get an answer, do 1 over x, and then times to the top, and then you don't stir.
That's actually work. Here we go.
It's the same amount.
Second answer, yeah, I guess so.
We didn't have second answer back then.
Well, you lived in the dark ages.
Thank you. Okay, does everybody figure out how this is done?
Insulate walls.
Oh, watch it, Colin.
They would put wood on the
Okay, so given the initial species of one, this is a second kind. So we can be given all of them and be able to find the answer real quickly. This is a second type. Given the initial pressure of one of the species and the equilibrium pressure of another, you should be able to find K. Now, we call this process ICE now. They used to use PO for P initial, PEQ for the equilibrium pressure. Now we just do initial and equilibrium. So ICE. I stands for initial, C stands for change, and E for equilibrium. So we gather the information, we write a balanced equation, and we construct a table, and it's an ICE table, and we solve it systematically or through mathematics any day now. Okay.
Reached at a certain temperature, a 1 liter flask contains only SO3 gas at a pressure of 0.85 atm. What is K for the reaction?
Okay, so
half it.
if at equilibrium, oxygen with a partial pressure is 0.226 is present. construct a table first with a known value. So you're going to do one like this. That's the old way. Now we just use ice.
Would they give you that if that?
They would give you something. So this is the old way we did it. We would now do it this way. Okay? We plug in what we know. We know that we started with this. We know that we didn't have anything else. And we know that equilibrium, we've got this. Everybody okay with that?
Oh, and then would you put?
Now, there's got to be some change, right? Which one's getting something and which one's losing something?
Oh, SO2 is probably gaining something.
Whoa. Okay, so, whoa.
Those transitions, though.
Okay, to fill in delta T, or the change, by putting a plus or minus. So we're going to minus something from SO3 because it's shifting, right? And we're going to add something to the other two because they're gaining something. And we know exactly what this one gained, right?
Right, because
Okay.
equilibrium.
Right. Now, sorry, it's going to build it again. Sorry. Made this a while ago. So what we do is we look at the coefficients. This is a 1, and these two had 2. So if 1 is this,
That by 2.
times it by 2, and you get the others, then you just add down and get your equilibrium any day now.
9, 8.
Okay, and then you make your K and plug in.
So you take from the E at the end.
Take from the E at the end to plug in,
So you get
because it has to be at equilibrium to find your K. So plugging in.
wait, oxygen is your.
So I like to also put my arrow here so I sort of know what's going on. There's my arrow. There's my plus.
Wait.
Except my plus didn't show. Try again. Yeah. It might have been flipped, but they told us we started with SO3.
But yeah, but wasn't it SO3 plus O2 equals SO2?
Nope. No. You just balance that equation.
Well,
It's just flipped of what's here.
On the last slide, I just thought it said that.
No. Okay, so we plug in, and if you plugged into your calculator correctly, you got this number.
Get it?
How do we do?
We did good.
Thumbs up?
We have our designated calculator man.
Well, you got to do it yourself too. Okay? Whoops, wait, what? So an ice chart, in the past, they've had this on every single year. The last couple years, they've started moving away from it, but it has been on 1 out of the 3 last years. So you need to be able to do it. Okay? All right, so let's look at another thing here.
Okay.
The third version. So the first one, they give us everything at equilibrium, we just plug in. The second one, they give us something initial, they give us something at the equilibrium, and we've got to figure out through the ice table and find the K. This one, they give us the initial concentration of one species and how much of that species was consumed. Recall again that the pressure is proportional to the number of moles of gas. If 25% of the gas is said to be consumed, then the pressure of the gas is decreased by 25% of the original value. You need to be careful because here is where they like to trick you. They might say 25% is consumed, or they might say 25% is left. So you need to make sure you understand what is going on.
So one would be
Okay, because
10% off and one would be 70.
right. Okay.
Oh, it's tricky.
So read careful to see if it was 25% used or 25% left. That changes things a lot, right? Okay. All right, so here's the example. Consider the reaction. Hydrogen gas plus iodine gas gives us hydroiodic acid gas. Suppose that we start with hydrogen gas at 0.2 atmosphere pressure and iodide gas of 0.1 pressure. When the equilibrium is reached at a certain temperature, 48% of the hydrogen gas will have been consumed.
So you have 52%.
So we got to figure out what's going on. Calculate K at that temperature. So we set up our ice chart again with what we know, and we decide what's going to happen here.
So
Sorry.
Could you put like a percent as what's consumed?
You want to actually have a number. So we know the change here.
Figured it out.
Yeah, we figured it out. So since 48% of hydrogen was used, the change will be 48% of 0.2. So if we take 48%, remember we're going to go 48 divided by 100, or 0.48 times that to get the 0.096. Now, in front of those, there was just one, so I know that iodine will change the same, and HI will actually double that, right? Because there's a 2 in front. So we get a 2 in front of that, and it's going to be added, and the others are going to be subtracted.
Take 40% off of 0.1.
Yeah, because it's only 48% of the hydrogen gas that was consumed, so that's really important. You can change delta P for using the balanced equation. Come on, just get it in there, do the arithmetic.
I can't do arithmetic.
And you've got your equilibrium, and then you can make your K and plug in. So make your K real quick and plug in, see what you get for equilibrium. We'll go to the next page. Products over reactants. Products over reactants.
192 over.
There we go.
As long as I do it both ways, so it's on the table.
I think it's on the next page, so I'm just going to bring it up again. Hopefully set it up this way. Remember, the top one's going to be squared
Squared.
because out of 2.
And you
Plugging in.
got, oh, please, 89.
Okay, it's really important that you get used to doing this and feel comfortable doing this so that when this comes, you're like, ice, boom, 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 done. Okay? Now, they do or have had in the very past places where these will be x's. The c's will be x's. And you've got to use the minus b plus or minus the square root of b squared plus or minus 4ac divided by b squared. Quadratic formula.
Quadratic formula.
Thing.
Negative b plus minus.
There's a little song that you can sing with it. But I haven't seen that enough to really force you to make that. Okay, we'll do a couple with them during class. Minus 4ac. All over 2a, that's right, not b squared. Okay, so application of the equilibrium constant. Why do we need an equilibrium constant? This tells us if this reaction will go. So the bigger the number, the more the reaction is possible to go forward, the way it's written. The closer it is to 1, so if it's very small, under 1, it's probably not going to happen. And if it does, it's going to take ages to happen. Okay? If it's very large, it's going to go fast. If it's at 1, it is at equilibrium. So it'll help you to determine the reaction direction. If we are not at equilibrium and we plug numbers into the K, we get what's called Q. So it's done the same, products over reactants. We do that to the exponent, but we call it Q. Now you had your hand up.
So can you have something over 2? I mean over 1?
Oh yeah.
Okay.
Yeah.
That would be the faster.
The bigger over 1, the more the reaction's probably going to go.
So
Okay.
SO3 is less likely to decompose than the H2 and I2 to make.
Right, because we had 89. Right, so 89 is going to go the way the reaction's written. The one that's 0.1, it probably wants to go the other direction than what it's written. Okay, so this is one, they are very, very, very particular. If you've got stuff that's not at equilibrium, do not call it K, call it Q. It's really important. So if you plug stuff in for Q, that's where I'm not at equilibrium. I can see how close I am to a K. Is it going to shift? What way is it going to shift on the reaction? Okay, so if Q is greater than K, this means the denominator is larger than it should be, right? And the larger was the top was the products. So I must need to shift more to my reactants. So it's going to shift back to my reactants. Okay. If Q is less than K, this means that my bottom's too big and I don't have enough products, so it's going to shift to get to equilibrium. It's going to shift from my products or my reactants to my products because I need more on top. Okay? So reactants to products. So they often ask you, and this is easily a multiple choice question. Okay? If I have a Q of this and a K of this, which way is this reaction going to go? Forward or reverse? Well, if Q is too big compared to K, and I need to get rid of products and need to have more reactants so to find equilibrium, it's going to shift back to the reactants. If Q is lower than K, then it's going to go forward. Okay? If Q is equal to K, then I am at equilibrium. It's not going to shift either way. Okay? I shouldn't say that. Equilibrium means as many is shifting forward as is shifting back at the same time. That's equilibrium. Okay? All right. So here's our reaction. Let's try this. So the K for this reaction is 6.2 times 10 to the minus 14. What does that tell us about that reaction?
It is small.
It is small. So it probably doesn't like to go forward as written. It probably wants to go reverse, right? Okay, so in this direction, in which direction will the reaction proceed at 200 degrees C if the original partial pressures are, so write me a Q. Tell me what the Q is.
So Q equals.
Q equals. Do a Q equals. Find it real quick. Products over reactants.
Divided by 0.52 times 0.124.
Wait. So Q would be 0.00. Yeah, if that.
Did we do it okay? You guys that hugged through? Okay, so compared to what it is it bigger or smaller? First of all, it's bigger, so I have more products than I need. So which way is it going to shift?
Isn't it still going to go backwards, though, because we're less than 1?
To get to equilibrium, this is equilibrium at that stage. So not very much is going forward. Most of it's going backward. But I still have to get to that. I'm not at equilibrium right here. So to get to this one, I've got to get rid of some of these. I've got to get more reactants and get less products.
Right. So it's going to shift left.
So it's going to shift this way. Yep, left. Oh, I've got an error there. 0.02. Yep, he caught me. There should be a 0 there. So, yeah, this should be right here. I got a typo. Double check it. How we doing?
Is this the same thing as what you got? I'm not sure.
-6.
Oh.
You got the same number as this? I just probably typoed it. Okay, so I just typoed it. Okay, let's go on. So since, I'm going to move this out of the way. Since this is bigger than K, the reaction goes from right to left or backwards, which we decided. Good.
Yeah, backwards.
Okay, moving forward.
Figure that out from the initial thing.
But we don't know where we are. We don't know if we had more. We don't know which way it's going. Okay, so equilibrium partial pressures. Given K and the equilibrium partial pressures of all species but one, in this case, a problem is a simple plug-in. So looking at what we've got, so say I had this reaction, and they gave me, whoa, right on top of that reaction.
K equals
Okay, there we go. Finally went in the right place.
25C. What is the P-no if P-no is 0.0?
So basically you would just write your K, plug in, right? So find your equation, expression, here it is.
Real bad.
So basically for this one right here, I'm putting in X, right?
Right.
And so once I've got X in there, and I'm just going to plug in everything I do know and solve for what I don't know. So it just is a simple algebra problem.
And then you just.
And then at the very end, I'm going to have to square root it, right? Because I'm going to have to square root it to get to X. So see if you can figure out the problem.
Times those together.
Calculator.
Times them together to the other side. That'll be your answer.
Huh? That involves moving. Yes, it does. That's part of being an AP. No. It's annoying.
Not really. Just times those two together and then times them over to the other side.
So
What's 1 plus 7? It's like
there you go.
8.
So how'd you do? Did you get it?
Wait.
No. Double check.
Wait.
Basically, you're just going to times both side, this side by this, and then you square root it.
Oh. Okay. See.
Got a square root.
You got a square root. I didn't see that. Are you smarter than a fifth grader?
There. There. Okay, we're going to take a brain break, and we're going to do a quiz. So grab a clicker.
What if we took that cube? Now I'm just confused.
Okay, so here's the problem. We've got the K, we've got the beginning pressure, so we've got I's. So if we plug in, start by making the unknowns. Okay, we have all the I's. If my I's will all come in. And we know what's going to happen as far as adding and subtracting. And we know if we say X in this, that the last one will be a plus 2X, right? I don't know how much it's going to change. But I can plug it in now, once I've got this, and get, remember I told you some of them we're going to need to use the quadratic, the minus b squared thing. So here we're getting this. Now, it's going to be pretty small. So what we do, let's see if we can go forward. Come on. Really? Okay, so the quadratic equation can be used to solve this problem, or you can graph it and find it. However, in this case, taking the square root of each side is a lot simpler because both of these are squared, right? So a lot of kids, when they do that on the AP exam, they don't think about that, and they're trying to do this big quadratic formula when all I had to do was square root both sides. So look for that first.
That's not your answer.
This is not my answer because what did we have in the ice? Right. It's merely the change. So we're going to take and put our ice back up here, hopefully. Whoa. It went away.
Getting on to the shot later.
Okay, so then we just...
Oh my gracious goodness.
Really?
Why you do
Okay,
this?
it doesn't matter if I've got a negative number for x. Oh my heck.
Go one more. One more. Just patience is a virtue.
But it's something I don't have.
There you go. See?
Okay.
Boom.
All right, so you can see real quickly that you can get equilibrium real fast.
So did they just plug in what they got for x into the equation and they solved it?
Right, so we had x in the first column, x in the second column, we had 2x in the third column, right? So even if I had a negative, I would still plug it in, and even though the negative in front, it would make it a positive. So I just go with what I have, okay? Then I just add these two, and I get my equilibrium. So that's what I would have at equilibrium. So that's another thing that they can do. They can say, here's the K, here's what I started with, what am I going to have at equilibrium? Nothing.
It's all going to blow up.
Okay. So the effect of change in the conditions upon the equilibrium system. So what happens? Le Chatelier. So Le Chatelier basically says if I put a pressure on a system that's at equilibrium, it's going to shift
The opposite.
to make that pressure so that I find a new equilibrium. So for instance, here I'm standing at equilibrium. If one of you were to come push me, I would force back to try and keep it equilibrium so I don't fall over, right? Same thing with the equations. So things that can disrupt it are pressure, if I have a gas. If I don't have a gas, pressure cannot affect it. Temperature always affects it. Doesn't matter if I have gas, liquid, whatever. Okay, concentration. If I add some more of one of the things, it's going to affect it, or I take some out. So it's going to shift to counteract the change. So let's see if we can bring this up. Yeah, really fast.
Oh my gosh, press too many times.
I know, I get impatient.
Where are you going?
I'm going away. Jeez.
Too far.
This is driving me
It's like you're
crazy.
like fast forwarding in the movie and then you don't press the play button fast enough and then you go too far.
Like in Lion King.
Come on, really? Okay, so qualitative changes. Adding or subtracting a product. So something we can add or subtract. So with Le Chatelier, we're going to add something to one side or subtract something from one side. I'm going to show you something really quickly. So I'm going to draw on this while this is up. So hopefully this will let me write. Okay, so here's a generic equation. This is how I remember how to do it. I always put my arrows going down, okay? So if I put some A in, then it is going to shift this way, which is forward. So it has to keep going the direction it was going, okay? If I take some B out, the arrow still had to go this way, so it would actually have to go this way to fill the hole.
Just think it's like a counterweight in the background.
Right.
You add
So
more,
if I add more of this on this side,
it's going to go down.
the arrow has to keep going that way. It's going to go that way. Okay? So if I do take C out,
Yeah.
the arrow had to keep going the way it was going, so it would go towards C. Okay? It's just a trick that I learned. If I took out C, the arrow has to keep going the same direction, so it has to go across the arrows and go down. Okay, you got it? If you can remember that, the multiple choice questions on Le Chatelier will go really fast. Okay? That has to do with heat and everything else. So and when we get to heat, yeah, if it's a negative heat or negative kilojoules for delta H, then heat is added to this side. So you can still do add and subtract heat that way, and it'll still tell you which way it's going. Okay, eraser, and hopefully it'll go away, and we'll go on. So that's just a real quick trick I learned to help with that. And hopefully that's all erased.
Yeah, perfect. Boom.
Okay, adding a species will direct it away from the species you add. Taking away a species will try and fill the hole. We already talked about that. Change in volume. So if I change the volume, that's going to affect the pressure. If the pressure goes down, it will go to the side that has the most gas. If the pressure goes up, it'll go away from the gases because I'm crunching it down. Okay, so if we go through this really fast.
When the volume is decreased, the reaction takes place in the direction.
Okay, in a balanced equation, if there is no increase or decrease in the number of moles of gas, if they have the same number of moles on both sides, pressure won't affect it. Or if there's no gas on both sides, pressure won't affect it. So increasing or decreasing the volume then would not increase or decrease one way or another. Okay? And that's all known as Le Chatelier. Okay, change in pressure, we talked about that already. If the change in pressure, if I have a gas, it will shift it away from the gas. If I don't have a gas, it will leave it alone. If I decrease the pressure, it will shift it towards the gas, the side that has the most gas. Change in temperature. If it's endothermic, then it will shift it. Endothermic would put the heat on the reactant side. So if I change the temperature, it'll shift. Depending on what I do to that, if I take heat out, it will shift towards the heat. If I put heat in, it'll shift away from heat, just like if I'm adding a substance or taking away a substance. You just need to know where to put the heat. Endothermic is on the reactant side. Exothermic, you put the heat on the product side. Okay? So as long as you know, and delta H will tell you if it's positive, it goes, I add it to the reactants. If it's negative, it's coming off the products. So that just tells you where heat goes. Okay? A decrease in the temperature does cause K to become smaller if you have an endothermic reaction. If you have an exothermic reaction, then an increase in K will cause it to become smaller. So just remember, products over reactants. If I'm shifting away, you can say, oh, I'm making my products bigger. What's going to happen to my K? It's going to get bigger. Or if it's shifting away from my products are going to be smaller. K is going to become smaller. Okay? So here we go. You guys are going to tell me. Okay? You're going to tell me with your fingers which way it's shifting. Okay, we're going to do old-fashioned. Which direction will it shift if more oxygen is added? Yes, that way. Because if I'm adding oxygen, the arrow is going to come down here and shift it that way, right? Okay, and it didn't show my other arrow. Okay, second one. Okay, what happens if SO...
3 is removed.
3 is removed?
That way.
SO3 is removed. It's still that way. Still the same direction. Okay, follow the arrows. If you do the arrows all facing down, then it helps. It really does. Okay, so it is going to shift from the left to the right. Any day nap. One. Okay, consider the reaction again. What happens to this if the volume is increased? Volume will affect what?
It will affect pressure.
Pressure. So if the volume is increased, what side is it going to go towards? The side that has the least amount of gas or the most amount of gas? Most. Which side has the most amount of gas? Which is the other side, Colin?
Right.
Wrong.
Left side.
You have 2 plus 1 is 3, and you have 2. This left side has more gas, so if I'm shifting to make a bigger volume, it's going to shift to the left.
Yeah.
More gas. Okay?
Oh, buddy.
All right, here's another one. The pressure is increased by decreasing the volume,
It's going to be the opposite.
which is?
Right.
It'll go to the right, right. So it'll go from 3 gases to 2 gases.
Make my L's.
Okay? All right.
Temperature is increased. Well, let me just tell you, first you have to find delta H for the reaction. Then
Yeah. So if the delta H is a negative 198.2, where does the heat go? Left or right? I don't even care what the heat is. The heat goes over here. Goes on the right of the equation. Okay?
oh, I thought
So if I am increasing the heat, I'm putting heat in, which way is the reaction going to go?
yeah.
Should have shifted to the left, away from it. So whatever side I put it in, it shifts away from that side to the other side. Whatever side I take it out of, it shifts towards that side. Okay? All right, change in pressure, quantitative. Come on.
Quality of.
No, I'm not patience. Okay, so here's an example again. We've got our, making our hydroiodic acid again, where we've got our K and we've got our pressures, okay, at equilibrium. What will the partial pressures be when the system reestablished equilibrium if the pressure of iodine is increased to be the same as that of hydrogen?
Well, let me tell
So how am I going to do this?
story about
Ice again. So we had initial, right?
yeah, you're just doing X's.
We're doing X's again. Only this time we know what we're shifting. We know, sort of. Okay.
So
Okay, so this bottom thing basically is saying 0.204 minus x squared. So I can take a square root of both sides. It's not showing everything yet. There we go. So I can take the square root of both sides. If I take the square root of both sides, I'm just going to go on to the next one here. Okay.
yep. And then it just reduces
It reduces. I can easily solve for x now.
X equals 0.135.
Okay, we substitute back in.
And you get
A very slow computer.
now 0.069 and 0.062
I spelled equilibrium wrong, but don't look.
equal.
Okay. Okay, changes in temperature. Change in temperature will not only shift the direction of the equilibrium, but it also changes the value of K. So pressure won't affect the K. Only thing will affect K is temperature. Okay, once we do temperature, then we're going to have problems. We're going to have to use the Van Hoft equation that relates the equilibrium constant to temperature. Here's the equation, something you might want to write down.
Van Hoff.
Van Hoft.
Oh,
Van
put
Hoft.
the T in the wrong place.
David
Van Hoft. I think I didn't capitalize it. I don't know. That's how they had it.
That's not somebody's name.
It's just his last name. That's how they name things, like Arrhenius. So quickly write this one down. This one needs to go in your equation book. Van Hoft equation. So if you know the initial K and you know the new K and you know the initial temperature and the new temperature, or you want to find the new temperature or you want to find the new K, this is the way to do it. But you have to know the delta H for the reaction. Okay, delta HZ naught is a standard enthalpy change for the forward reaction as written. For the one that we want to work with, let's see, no, R, this is the one that is the 8.32 joules per mole Kelvin. This is the R that is more the thermal or the energy R. Remember I told you you'll be given R's on your equation sheet. You've got your equation sheet. You know there's like 5 or 6 R's. You need to identify them by their units. Okay, so the gas law that R that we have is 0.00821 atmospheres times liters divided by mole Kelvin. You need to identify that different from this one.
What would be a good letter?
For that R,
Yeah.
something with energy. So E, I guess, I don't know. I don't think we have an E. Okay, consider the reaction. Here we have the K is this at 445. Calculate the K at 23 degrees. So we're going to have to use the Van Hoff. We're going to have to use a table for the delta H. We're going to grab all that. So we're going to get delta H, and it's right there. And we'll do delta H in a little bit, a couple days, so you'll be able to get that. We substitute in the equation everything that we've got, and sorry that bottom shifted a little bit, and we're going to solve for K1.
Wait, whoa, you did a lot of things.
I did a lot of things.
What was the constant again?
Constant was 8.32. Okay, and then you should be able to opposite log or base E each side.
Oh, that's so hard.
Now, have I seen this one on the AP exam? Yes, maybe once. It's not something I would really stress out of.
Don't worry about it.
What is
LN?
LN? LN, yeah.
So it's inverse.
It's base E. It's base E. Okay, so going forward, hopefully this will just take me one forward. We'll see how far more we can get really quickly. The smaller equilibrium, because it's an endothermic reaction, temperature is decreased. Okay, so that is the end of that one, which is what I wanted to make sure we were at. Review constantly, finish your homework. I am going to make sure that we have a review quiz every day. Sometimes I'll use it a break quiz, sometimes I'll use it at the beginning, sometimes I'll use it as an exit quiz, but we will have a review one every day. Okay? I am going to give you some actual problems next time that we're going to work through, practice ice, do some actual hands-on stuff, trying to get calendar tweaked a little bit so that we can get everything done. 2 homeworks for you.
Oh no.
They're fairly easy.
They
Ready?
Be like, go look at a tree and tell me.
Number 1, design an AP shirt for us for this year.
Oh, I already did that in biotech.
So design a shirt. Take a piece of paper on the front, do the front of it, on the back, do the back.
On a website. I have a website.
You can do a website, just print it out and bring it in. Okay, that's number 1. Number 2, I can't remember what number 2 was. Oh, let's shut this off.